Okay, now let's discuss one of the established CNN, which is AlexNet. Okay, we just discussed it roughly. We don't want to go deep into the detail on the architectures. Okay, that is the AlexNet architectures. As you realize that, okay, again the input image, okay, again AlexNet is designed for image again. That's why the input is the image. So the image there, the size must be 227 times 227, of course time 3 as a depth size. Okay, that's mean if you, let's say you want to apply AlexNet to your to implement the AlexNet into your application, then if you capture image which is different size with the different size as compared to this input size image of AlexNet, then you need to resize your image, or you need to shrink your image. If you capture too big, then you need to shrink or resize your image into 227 times 227. Okay, because it's only support that size of image. And again, the format is, the depth is equal to 3, then means that the AlexNet support the color image only. But that does not mean you cannot apply it for grayscale image. There's a tricky behind it, because actually my previous FYP also implement this AlexNet. Okay, but I'm using grayscale, still can be done by using AlexNet, but you need do some tricky things first to make sure that your grayscale become color format image. Okay, but originally AlexNet is designed for color image, so that's why a color image with the size 227 times 227. So that's why if you want to implement this for color image, it should be suitable for you, because actually the input here should be color image with the size 227 times 227. So you can see there, the first approach, the first operation is a convolutional layers there. So you have a 11 times 11, that is refer to the to what, to the, what is this 11 times 11 is what? This is the filter size, 11 times 11, and then the stride equal to 4. Okay, so from there, then you can estimate the why it at the after you apply the convolutionals there, it will shrink into 69. You can count it, 11 times 11, and then stride equal to 4. Then I hope you can count, is it how actually from that you can produce the size is at the end. I'm sorry, the size of the at this convolutional layer, the filter size is 11 times 11, and then you have stride equal to 4, and then this 96 is not is actually is number of filter, meaning you have a 66 filter of 11 times 11. So if you have a 66 filter 11 times 11 with stride equal to 4, of course you will produce the depth there equal to 96, because of the filter size equals to 96. But how actually you can compute 55 and 55? So can you try to estimate that? Can you try to estimate that? How actually you can produce that 55 times 55 according to that this AlexNet architectures? Okay, you can see that that's how it's actually they count it. Okay, 227 minus 11 divided by 4, because you jump 4 steps ahead, so that's why you need to divide into 4 and then plus 1, and then you can see that 227 minus 1 here, when there's no padding mentioned, that's mean no padding. Okay, if there's no padding element mentioned in this convolutional layer, meaning there's no padding. So meaning that if you apply 11 times 11 without no padding, then the image will shrink. Okay, and then it shrink, and again because your stride is more than 1, it will keep shrink. So that's why the 257 from the 227 times 227 it shrink into 55 times 55. Okay, because there's a two element make the size shrink. One is because of no padding, another one because your jumping size is equal to 4, or your stride size is equal to 4. Okay. Okay, I will try to explain how actually how can we calculate the volume of this one instead of you are using this formula. Okay, it's better for you to go to the previous slide, that the summarization slide, because that is the general formula to estimate the volume of the output matrix after apply the convolution here. But you need to remember that the spec of your convolution layer, the parameter involved there, the description of your convolution layer. Now the convolution layer in this area, the size of the window or the filter is 11 times 11, and the number of filter is 96. Stride equal to 4. Because there's no information about the padding, then that's why we assume no padding. Okay, in this stage there's no padding. So if you want to know how actually you can calculate this one, how actually the size have been shrinking into from 27 to 55 here, we already discussed that in the previous slide. But of course, if you if this is difficult for you to count, you can use the general formula. That is more easy. Okay, go back to the general formulas there. Where is the general formula for this convolutional layer, where you also consider the padding as well as stride there in your convolutional layer? I think it should be this slide. Okay, that one is talking about the stride, convolutional stride, padding. Yep, this one. Okay, this summarization represent the formulas how to calculate that. Okay, I just show you one example which is related to the first convolutional layer of of your AlexNet. Okay, later you can try also the others layer inside the AlexNet architectures. Okay, I just show you. Okay, again, if you remember AlexNet, the slide there that I show in because I don't want to open that slide, is too far at the end of this my slide note. So we just focus on this. If you remember AlexNet, the input size there is 227, so that's why the input volume matrix should be 227 times 227 times 3. So your W1 equal to 227, H1 equal to 27, and your D1 equal to 3. And then K is represent the number of filters. So again, that convolution involve 96 filters. So 96 number of filters. So that's why your K equal to 96. And then what is F? F is represent the filter size, because the filter size there is 11 times 11, so your F equal to 11. And then your stride in that convolutional layer is equal to 4. And another one is padding. Since there's no padding information about that convolutional layer, so there's no padding operation involved. So that's why you put the P equal to 0. And then once you get all this information, in order to estimate what is the output dimension in terms of your width there, W2, okay, which I think which there is a x-axis size, okay, h here is a y-axis size, so d there is when the depth, which is z-axis size. So just to find the output width there, I just show you one example. Later you can compute all w2, h2 as well as d2. Okay, for w2 you apply this formula. Okay, this is the formula, and then I just fill in the numbers in this formula. This is the numbers that I fill in. At the end I get 55. So later you can compute the h2. Okay, you will also get the 55 there. And then about the d2, again is depend on the number of filter k, so that's why d2 equal to k, which is equal to 69. So that's why the volume after do the convolutional operation, the first convolutional layer for AlexNet, the volume size of input image is 227 times 227 times 3. After the first convolutional layer, it become 55 times 55 times 69. Okay, so that's how we calculate that. Okay, so I just show you that one example. Okay, that is the how it can be, you can calculate the output volume size, or the size of matrix of the size of the output matrix after the convolutional. Then later you can try on this one. Okay, maximum pooling. Of course, the maximum pooling you need to use the general formula of pooling layers. Okay, don't use the convolution layer, otherwise you don't get the answer that then you will go into that. Okay, for this one you can try the general formula for convolutional the convolutional operation. If the input size is 27 times 27 times 96, how do you get 27 times 27 times 256? Okay, if you see there, the padding equal to 2, because the filter size is 5 times 5, and the padding equal to 2 means that the size is maintained. Okay, 227 times 227, 227 times 227. Okay, the one which is changing is the depth size. The depth size is 256 because the number of filter is equal to 56 here in this convolutional layer. So that's how it's work. Okay, normally there's no standard way to describe the architecture. Sometimes people try to to draw it in this way, so it's easy for you to interpret because you already see the you already see the volumes there, or the pictures of the input matrix and the output matrix, so it's easy for you interpret. Sometimes people not using this representation, they are using this description in order to represent the architecture of your CNN. This is the how you write or the architecture in text to represent the architecture of AlexNet. Okay, first is input 227 times 3, so this one is referred to this one. The second layer, which is convolutional, the first convolution layer, that's why they call it convolution number 1. So the convolution number 1, then you have 69 filter with the filter size 11 times 11 at stride equal to 4, padding equals to 0, means that no padding. Okay, this dimension is just show you the output after this operation. Okay, that is also another standard way. I don't call it a standard way because there's no standard way to represent the network architecture. Sometimes people drawing, some people doing in text. Okay, but if you are doing in text, it's better for you, especially if you want to translate this into programming, because later in programming, in order for you to write the architectures, you must know each and every layer what are the spec. So if you know the spec, then easy for you to write the code, because the code, if you are using the well established library, then it's almost the structure is almost similar like what you write over here in human in human readable format. Okay, I can just consider this tag as a human readable format. So if you apply some library, I think for those who might have experience programming the deep learning, one of the easiest, if you are programming using Python, one of the easiest library to design the CNN is by using the Keras. So the Keras structure, it's similar to what we write over here, meaning that you need to call the layer, and then you need to key in all the argument there, or all the input parameter that describe the spec of that layers. Okay, you must mention is you want to design a convolutional layer with 66 number of filter. The size of filter is 11 times 11, stride equal to 4, and no padding. So that is the element that you need to know. Okay, so that's why in term of human interpretation, is better to see in this type of architecture where you in this representation where you see all the picture, all the process involved. But in term of writing the programming, then this one quite be better, because once you know the spec, you just write it in that programming language, then you can have your filters there. Okay, so I think you can just check back there. Okay, this is the first convolution layer, that's why they call it convolutional one. And then this is the first maximum pooling layer, so that's why they call it maximum pooling number 1. And then the filter size is 3 times 3. Of course, maximum pooling, you don't have many number of filter, because the filter itself don't have a filter coefficient, just the size. And then again, like I said before, it's very rare to see maximum pooling layer consist of padding. Okay, normally we just see the stride. Okay, that's why there's only stride, but there's no padding. Normally padding is designed specially for convolutional. And then normalization layer, again, this is also referred to the batch normalization. You can see that they are applying the normalization is after the pooling layers, but again, this is AlexNet. Like I said, because they find out, might be in during the design the AlexNet, they find out the best way to normalize is at this level. But like I mentioned in when I discussed about batch normalization, later when you design from scratch, normally people will put a batch normalization is either after this convolution, or convolutional layer, or inside the convolutional layer, which is between the convolutional operation and activation function. Okay, you put the batch normalization at in between that, or you can also put after the activation function, which is after the convolutional layer. So that is the two position where people try to put a batch normalization. But because this is the well established architecture, so that's why you can see that the normalization also sometimes they can also put any position that they don't want. But later you in our syllabus, if you talk about batch normalization, just focus on batch normalization is always involved. Is it either inside the convolutional layer, which is between the convolutional operation and activation function, or you can also put after the activation function. Okay, so you have a normalization layers, and then this is a second pooling layers, and then you have another normalization layers, and then I think this one should be the last one before you have a fully connected layer. No, this one, yeah, we have, yeah, this one is convolutional number 3. You have 1, 2, 3. Okay, I think there's yep, there's a convolutional layer 3 times 3. Okay, I think this one is not complete. Okay, you have a convolutional number 1, convolutional layer number 2, this one number 3, so this is number 3, this is number 4, number 5, and you can see that you can see that it will end up with fully connected layer, which is FC here. There's a two fully connected layer there. FC, fully connected layer before you decide the you decide what type of you decide what actually this image is it, okay, or the output here is a label of this image, okay. But AlexNet is actually the output consists of 1000 classes, meaning that you put any image, it will give you the label of this image, where the label of the image can be either one of this 1000 label or 1000 classes. So that is the AlexNet, the architecture of AlexNet. Okay, original well-established AlexNet, the input is 227 times 227 times 3, and the output is 1000, which represent 1000 classes of image. Okay, meaning that the input is image, it will classify this image is suitable to be labeled in this 1000 classes, which this image belong to in this 1000 classes. Okay, so it had been introduced in 2012, and then again, this is we're talking about one of the largest and well-known data set, which is known as a ImageNet. Okay, I think ImageNet at that time, or because it keep updating the data set. Okay, but for AlexNet, it have been trained with ImageNet, where this ImageNet consists of almost 6 million image. Okay, meaning that you have a 6 million data set consists of 6 million sample or 6 million image, and from this 6 million image, this 6 million image have been labeled with 1000 class, or have been labeled with 1000 label. So that's why when they designed the AlexNet, the output there consists of 1000 output that represent 1000 classes. So that's why this can be considered, AlexNet can be considered as one of the well-established architecture, because of course, to you have a 6 million image, and then by applying AlexNet, do some training, and AlexNet managed to provide the high performance classification. Even of course is a top 5 error, I think. Yeah, in 2012, by reducing a top 5 error, okay, from 36 to 50.3%, and then of course by having a huge number of image, and have a capability to identify and classify according to 1000 classes, that's make the AlexNet become a well-established CNN. Of course, after that, it is already have been beat by many new well-established, well-known CNN such as GoogleNet, VG16, VG19. I think there's a MobileNet as well, and so on. Okay, so you can even see that how actually they have been trained. Okay, AlexNet was trained in 6 days, okay, simultaneously by using NVIDIA GeForce GTX 580 GPU. So I think the latest latest budget laptop, we have that spec. You can you can do that, but you need to make sure that you don't turn off your computer for 6 days. I'm sorry, you cannot do that, because at that time 580 GPU is, they are using a double, means that you have they put a 2 graphic card in the motherboard. 582, you have a 2 graphic card GTX 582 on your motherboard, then you can do what this Alex do in order to produce the AlexNet. Okay, and even you need to have a big memory, because you have a 6 million image. So at the end, they produce the what you call the AlexNet, then they share with us, to the community, so you can to borrow the AlexNet to do other application. Later I will show you example, because in programming later I will show you, in order for you to develop application related to CNN, you can make it in, you can develop in two way. One is you can develop from scratch, meaning that you are designed your own architecture one by one, and then before you can train by you to solve your problem. Another one is you can borrow the architectures, the well-established CNN architecture like CNN or other new well-performant architecture to solve your problem. So that is the best approach in applying CNN, because you don't have to have a powerful computer to do it, because once you borrow the AlexNet, for example, AlexNet is already have been trained and have a capability to classify 1000 classes. Then if you want to solve your application, which is small and not challenging as compared to this 6 million image from the ImageNet dataset, so of course AlexNet have a high capability to solve that. Okay, because AlexNet is more than that, can do more than that. So if you just want AlexNet to solve your small problem, of course for sure that AlexNet can do it. Okay, we will discuss that later.